if you see the simple system and you take a look at the equation, you can see that what you're looking at is, if you know the input and the output, then you know the change. So if you know one and the other, you can calculate the third. So it's important to understand that input this equation, which actually could be rewritten to, as you can see in the reading here, you could rewrite it as a change in a certain amount of time for the reservoir is equal to the input minus the output over that same amount of time. Well, I think that's pretty simple, pretty straightforward. All right. But what's interesting is that you don't have to stick to this this idea of liquids, as in with the initial bathtub idea. You can talk about bank accounts, as in the example in the text. You can look at trees. You can look at fossil fuels, or you can look at pollution and pesticides. So what you can do is you can say, well, if I have a certain amount of water coming in, right, from the spigot, and I have a certain amount of water going out, and a certain amount of water going out as through the drain, then the amount going in and the amount going out are equal. Then the compartment stays the same. The bathtub, the amount of the water stays within the compartment. But if let's assume in this example that the input got bigger. If the input got bigger and you can't get any more out, well, you're going to have an overflow. Either your bathtub is going to overflow. And in a sense, the compartment's gotten bigger. Instead of just the bathtub, you're talking about the bathroom is now filling with water. Now, when you're looking at another example, is in here, where your input and output, all right, are equal. In this case, they're perfectly equal. And the example they're using are the number of trees. Like, say you have a forest that has 1,000 trees. For every one you cut down, you plant another one. So your forest will always have 1,000 trees. So that compartment, in this case the forest, has a certain number of a certain amount of material, in this case the trees, and that amount doesn't change because input and output are equal. So if you think about it, if input and output are equal, this value is 0. When this value is 0, what happens to I and O? They're equal. So let me show you what I mean, and I think you probably already know, but I'll go ahead and say it. I equals O, and when I equals O, change in S equals 0, right? And let's look at what change in S equals I minus O, and if I and O are both the same, let's call it 5. 5 minus 5 equals 0. And what is I equals O plus or minus 0? Well, this I equal O. In this case, 5 equals 5. Well, that just makes sense, right? So mathematically it works out. And I think intuitively as well. I think if you think about it intuitively, you'll see that that when these two are equal, when input and output are equal, there's not going to be any change in that compartment or in that reservoir. Now in C, letter C, you have to think about, what if the input is smaller than the output, like in the case of fossil fuels, which is the example they're using. We're pulling a lot of fossil fuels out of the earth, but there is virtually none going back in, at least not in the time scale that we're talking about. And so the reservoir of fossil fuels is drying out, and eventually will dry out. I mean, it's just plain logic. Now, the last example is when you have the input is greater than the output. So let's say there's some pesticide that gets in the sediment. So it doesn't leave the reservoir very easily. But the input keeps coming in, but it's leaving very slowly because it's in the sediment, it's not in the water. Or maybe the lake It doesn't empty very well. It's in the water, but the water doesn't flow anywhere. And the pesticide keeps coming in to the lake. So the reservoir grows and grows and grows. The amount of pesticide grows and grows and grows and becomes more and more dangerous. And so for that reason, this would be the input is greater than the output, and your change in S is getting bigger. So the change in the compartment is getting bigger, as in this form of the equation here. All right, so now knowing that, understanding that, let's look at the next type of calculation that we're going to have to do. You have to understand this, though, before you can understand the next part. Okay, so when we take a look at art, I think the big problem that people are having is that the notations don't follow the notations you've been taught in mathematics. specifically this mess here. I mean, I even think that this might be a typo because I'm not sure why it states it the way it does. This is correct. I think this section here is correct, but this per year I don't think should be there. So now let's go ahead and take a look at what art should be. And you can look at the example on page 46, figure 3.7, as rationale for my thinking. So when we look at art, and art is going to be the average residence time. Art is how much time does the stuff stay in the compartment or the reservoir. In this case, it's water. Art is going to be in that reservoir by the total numbers, the size of that reservoir divided by the rate of transfer within that reservoir. So if we take a look at what is the size of that reservoir, the size of that reservoir is here. It's 0.6 kilometers cubed, which is an amazing number to me. So about a half a kilometer in all three directions is how much water is inside this this reservoir. And you divide it by the flow rate, which is in this case is 31 kilometers cubed per year. Now this is a fraction, and if you remember correctly from math, when you handle a fraction, you can invert and multiply. So if you have 0.6 kilometers cubed, you can invert that 31 kilometers per year and multiply it. This, and remember from Mr. Decepeda's lessons with dimensional analysis, that this becomes over 1, and now you're multiplying 1 year divided by 31 kilometers. I'm inverting cubed. I'm inverting this fraction, this 31 kilometers per year, and I'm saying I'm going to multiply by 1 year over 31 kilometers cubed. And of course, when I multiply, what it turns out to be is it's 0.6 kilometers cubed year divided by 31 kilometers cubed. Okay? And when you do that and you cancel things out, you'll see kilometers cubed cancel out. And so what you end up with is 0.6 years divided by 31. Now, that's where I think they made a mistake. I just don't understand where this notation comes in at all. Maybe it's a different type of notation I'm not familiar with. In any case, if you take 0.6 and divide it by 31, you're going to get rounded 0.19, and of course that's 0.19 per year, right? 0.19 years. That's not 0.19. That should be 0.019. So really what we're talking about is 0.019. So 0.019 then becomes 0.019 years is equal to about 7 years. I mean 7 days, 7 years, Jesus. So 0.019 years is equal to about 7 days. And that's where they get this. That's where they get this 7 days, about 7 days. 0.19 is about 7 days. And how do I know that? You just take, just so you know, it's kind of a simple thing, and I'm sure you do already, but I'll do it. It's 0.019 times 365 days. And if you do the math, that equals approximately 7 days, right? So the math here, the notation is a little weird, but the numbers work out perfectly. And so again, I'll say that the dimensional analysis really could use some help. The notation could be more like what you're used to, but it is possible to do these calculations and use the notations that we just discussed. So when we're looking at the art for a larger volume of water, the way you see that the writers discuss it here in this paragraph, you can take and look and say, well, if we were looking at Garrison Dam, and again, if you look on Figure 3.7, Garrison Dam is 23,800,000, right? 23,800,000 acre feet. And you would do that same calculation that we just did, which in this case, instead of 25 million acre feet, instead of 492,000 acre feet, which was the size of the reservoir there, the size of the reservoir is going to be 23,800,000. If you did the calculations, then what you would end up with is, they're saying, it would take almost 347 days for that water to go through the system. And how would you do that? You would just set it up just like you did with the previous problem. You would take ART, which is equal to the total reservoir, which is S, divided by the rate of movement. The rate of movement stays the same. And so you'd have, instead of 492,000 acre feet, you have 23,800,000, and then you go ahead and you divide it by 25 million acre feet, and you'd end up, well, let's go ahead and do it. And if you take 23,800,000 and you would divide it by the 25 million acre feet per year, which is 25 million acre feet per year, right? You would get 0.952 years. I want to say again that what you're doing is you're inverting this fraction, which is 25 million acre feet per year, and you're inverting it and multiplying. So you end up dividing by 25 million, but the acre feets cancel out and your years on top. And if you take 0.952 and multiply it by 365, what you get is 347.48, which is what the paragraph is telling you you're supposed to get. So again, the calculations are correct, the formula is correct, but I just think the notations are confusing a lot of you. Okay, so here let's take a look at this. They're saying that there's this poison MTBE, which is added to gasoline, which ends up being dissolved in water, and it moves with the water. And then they make this hypothetical lake that has a reservoir of about what does this look like, 1 billion meters cubed, and they're saying that the flow rate is 10 meters cubed per second through this mythical lake. And what they're saying is that you can take this, right, 1 billion, and you can move the decimal, and you can say it's 10 to the 9th meters cubed. So if you move it 1, 2, 3, 4, let me do it with a pen. If you do it 1, 2, 3, 4, 5, 6, 7, 8, 9, it's 1 times 10 to the 9th, right? That, remember that scientific notation. Oh, Mr. Desipater's class. the memories. All right, so 10 to the ninth meters cubed. And what you have here is 10 meters cubed per second. Now there's that fraction again. And remember, when we are divided by a fraction, we can take this and we can invert it and multiply. Remember that, because you're going to see it happen. Again, here my issue is that here's this notation again. Why is that line there? I don't know. We'll try to see if we can figure it out. So the units meters cubed cancel out, right? So because you inverted and multiplied, in other words, let's see if I can make this make a little more sense. If I take this fraction and this is the same thing as 10 to the 9 meters. Let me rewrite that because I don't like the way that looks. Meters, let me just erase the whole thing if I can, yeah? All right. So rewriting this, we can say that ten to the ninth meters cubed, all right, is the same over 1 multiplied by 1 second, because I'm inverting this. Remember, I'm inverting this. 1 second, which is SEC. Remember the 1. We don't have to put the 1 in front of any variable. The unit, you can think of it almost as a variable. 1 second divided by 10 meters cubed. Okay. When we go ahead and do that multiplication, that's 10 to the 9th meters cubed second, SEC. It's multiplied by, divided by 10 meters cubed. What happens to the meters cubed? Well, I hope everybody can see that they're going to cancel out. And what are we left with? We're left with 10 to the 9th seconds divided by 10, which is equal to 10 to the 8th seconds. And that is what you see here. You see it right there because that's how they got that calculation. So that's the time. So how do we convert it to years? Well, we're going to go do that whole dimensional analysis again, which is kind of cool that it comes up again. I'm going to make sure I send a copy to Dissipated so you can rub it in your noses. And you see that we set up the equation to say we want to go from seconds, right? How many seconds in a year? Seconds per year. 60 seconds equals 1 minute, minute, hour, hours, day, days, year. So what you get, because you set it up this way, you want to get to seconds, years. This is where you want to get to. So the point of them putting this here is this is your goal to get seconds, years. You can see it. You can see that the goal is here. Then we need to be able to cancel things out. Well, do days cancel? Sure do. This cancels out here. Does year cancel? No, it doesn't. We don't want it to. We want it at the bottom. Is it at the bottom? Sure is. Let me go ahead and put that in green. Sure is. All right. Does hours cancel? Sure does. It's out, right? Do minutes cancel? Sure they do. And so the only thing left is the year here and the bottom and seconds at the top, which is what you see here. Which is what you see here, right? Seconds at the top and year at the bottom. And when you do that calculation, you end up with 3.1536 times 10 to the 7 seconds per year, which is fine. All right. So then the ART for Big Lake is 100 million seconds. Where do we get that 100 million seconds? Right? Let's count the zeros again. It's always nice to go ahead and count the zeros. That's one. Oh, let me undo that. Let me go ahead and reduce the size of that. Let's do that again. It's 1, 2, 3, 4, 5, 6, 7, 8. 1.1 times 10 to the 8th. Where did we see that before? Where is that number? 1 times 10 to the 8th. There's our 100 million, right? So our 100 million was calculated up here. All right, that was 1 times 10 to the 8th. But then we're taking it and we're dividing it by 31,536,000 seconds per year. Well, where did we get that? Well, right here. That's our calculation. Why are we doing that? Because we want to know how many years this art would be, right? And when we do it, and we go ahead and do the multiplication, the division, what you end up with is the seconds canceling out, because remember this is going to be inverted and multiplied. So I'll just do the calculation down here if you don't mind. What you see is that if you take the seconds and you divide it by seconds per year, if you invert this, that's the same as taking seconds and dividing it by 1 and multiplying by year over second, right? Because I'm inverting and multiplying. What happens to seconds? They cancel. And what am I left with? Year. And that's what you end up with here. That's what bothers me about this thing here. This line should not be there. That's a mistake in my opinion. So what happens is that when you invert this and multiply, here invert and multiply, you end up with 3.17, because the 10 to the 7th, 10 to the 8th, they cancel each other out. So you end up with 3.17 years. So okay. So you can use your graphing calculators, and you can go ahead and verify that the calculations are right, and they are. And that's for water. So this side's for the water. And the whole point is that if it's true that the MTBE is moving with the water, then they should both have the same art. They should both have the same amount of, in a given reservoir, they should have the same amount of residence time if the MTBE really is moving with the water. So we go ahead and we do the concentration of MBE, and we look at C, and we see instead of dealing with meters cubed, now we're dealing with micrograms. But even though the units have changed, the concepts have stayed the same, right? The concepts have stayed the same. What you have is this multiplication, and what is the multiplication? Well, it's going to be the volume of the lake, which is 10 to 9 meters cubed. You saw that volume being used over here, okay? And you have the concentration of this particular substance, which is 10 micrograms per liter. And what we do, and of course they get the calculation. Okay, so this is not really evident, like where this term came from, at least not very quickly. That's because they took it apart and converted the units without telling you, okay? So you see here they say 10 micrograms per liter. So that's 10 micrograms per liter. And if you think about it, a liter is actually 0.001 cubic meters, right? So 1 liter, hold on a sec. Let me erase this if I can. No, okay. So I guess this is all going to act up. All right, great. Not gonna erase. Okay, so if you think, as I said, a cubic meter is 0.001. So 1 liter is equal to 0.001 cubic meters. So that also says that if you think about the reverse, 1 meter cubed is equal to 1 or 10 to the third 1,000 to 1,000 liters, right? Now, the other thing that makes things difficult is their choice of fonts. This number 1 is actually the letter L. So that's liters, okay? Wow, that's annoying. And this is 10 micrograms per, and of course that's an L. But here, the same symbol is a 1. So it can be very confusing if they're not careful, and they weren't careful in this case. So just a couple critiques here on how they handled their fonts and how important it is to be careful, how important it is to be neat when you're doing your writing. So in any case, 10 to the third liters. So these numbers, all these numbers are just conversions. And as we go through and look at where they got each of these numbers, let's go through and do that. You see that 10 micrograms per liter, that's where they got this, right? It's 10 micrograms over 1 liter. We want liters to cancel out. So because we want liters to cancel out, we put our 10 to the third liters. Where do we get 10 to the third liters? That's how much a meter cubed is. So a meter cubed, we're changing a meter cubed into liters, right? So we're going to get rid of liters. We're going to get rid of meter cubed, and we're going to cancel them. So you'll see that meters cubed cancels here, right? Because remember, you must remember that this is all over the number 1, right? 10 to the 9th. Where did we get this? This was the volume of the lake. All right. So meters cubed cancels out. Micrograms is the only one left. Liters cancel out, of course. So then what you end up with is this number here. I'm going to go ahead and use a different color. What you end up with, I was going to use black, but I'm not going to. Here, I'll try to use this Technicolor one. 10 to 9th, I guess it's black. All right, times 10 to the 3 times 10, which is 10 to the 1, right? 10 to the 1 is 10, right? So what's 9? And remember, when you're multiplying exponents, you add the exponents as long as the base is the same. So 10 to the 9 plus 9 plus 3 plus 1. 9, 3 is 12, plus 1 is 13. That's where they get 10 to the 13. Why micrograms? Because that's the one that's left. You see it's there. It's left over. And if you do the calculations, if you look at micrograms, 10 to 13 micrograms is the same as 10 to the 7th grams. And we could do the dimensional analysis for micrograms if you like, but I think you've had enough of that. So this is an issue of conversion factors and of dimensional analysis, and there's been, that's probably what's caused most of your headaches. So if you have 10 to 7 grams, again, converting grams to kilograms, 1,000 grams in a kilogram, you go ahead and do that conversion factor, is 10 to the 4 kilograms. I'll go ahead and do that because that's easy. That's just pretty straightforward. So 10 to the 7th grams. If you want to know how many kilograms it is, there's 1,000 grams in a kilogram, right? So 1,000 grams, and that's 10 to the 3rd grams in 1 kilogram. 7 minus 3 is 4. And so grams cancel out. And whenever you divide exponents, as long as they're the same base, you subtract them. So it's 10 to the 4th kilograms. All right. That's where they got that. So that's where this number comes from here. So it's 10 to the fourth kilograms, which turns out to be, again, you do another conversion, so it's 10 metric tons. 10 metric tons is a big deal of poison in the lake. So the output of water, so far, that's what we would guess is in the lake based on these conversion factors. The output of water from Big Lake is 10 meters cubed per second. That's in the initial paragraph. If you go ahead and read on page 47, right? You can go and read for yourself. If we take a look at the transfer rate at grams per second, if we take a look at 10 meters per second, 10 meters per second cubed, 10 meters per second, 10 meters cubed per second, and we go ahead and take 10 to the 3 liters per meter. Again, we're converting, getting rid of that meters cubed. There's the concentration of 10 micrograms per liter, getting rid of liters. That's 10 to the 6 micrograms and per second, because if you look at the cancellations, meters cubes cancel, liters cancel. The only thing left is micrograms, micrograms cancel. The only thing left is seconds. And actually, I'm disturbed by the fact that they say grams is there. They left off. They left off. Wow, they just messed this up completely. I have no words for this. All right. Where do I begin? Well, this should have been grams. This 10 grams should have been down here. So that's just wrong. So if we do the conversion factors correctly, which we'll go ahead and try to do now. Let me see. We'll go ahead and try to do this correctly. All right, so if you set it up, it's 10 meters cubed. That's correct. Per second. That's fine. And you're multiplying it times 10 cubed liters. I'm going to put big L because I don't like that little L stuff. I have another word, but I'm not allowed to use it. Meters cubed times 10 micrograms per liter times 1 gram equals 10 to the 6 micrograms. Okay, that's the correct way of doing it. You see the micrograms cancel out. You see that the meters cubed cancel out. You see that the liters cancel out. If they would have done this dimensional analysis, they would have found out that they were wrong here. Okay? And you would have multiplied 10 times 10 to the 3 times 10. Right? Then that's 10. You're adding those exponents. Remember, you're adding. You'll have to beg my pardon, but I'm going to go ahead and bring this calculation down one level over here. So this is going to come down here. I know I'm crossing the space, but they don't give me any space. Oh, you know what I might be able to do? Hold on a second. Yeah, I can do this. Yeah, let me do that. Instead, then, let me do this and do this. Move it over here. So really, let me do the analysis over here and say I have 10 meters cubed over seconds. Again, we know that that's correct. 10 meters cubed per liter, and I'm using the big L, meters cubed times 10 micrograms per liter times 10 to the 6th micrograms. Okay, we see that this is grams. All right, grams. They didn't put the grams here, and this should have been down here. So if we do that, we see that micrograms cancel out, liters cancel out, meters cubed cancel out. When we do the multiplication, 10 times 10 times 10 to the third times 10, that's 3, 4, 5. Oh, look at what I did. I just copied, and because I copied, I got that number wrong. Think, Mendoza, think. 10 m cubed divided by seconds times 10 to the cubed liters, meters cubed times 10 micrograms over liter, 1 liter, and that's fine. Times, now this is where they got it wrong with that. I just copied and got it wrong again. And that's it. Grams should be on top, micrograms should be on the bottom. That should be 10 to the 6 down here and 1 gram up there, because there's 10 to the 6 micrograms in 1 gram. They messed that up. So if I add then the exponents of 10, which is 10 to the first, plus 3 plus 1, right? That's 10 to the 5th power. The liters had already canceled out. The meters cubed have canceled out. The micrograms are canceled out. So it's 10 to the 5th grams, right? Divided by 10 to the 6th seconds. Okay? And when you subtract that, what it equals is 5 minus 6, I hope everyone knows, is 10 to the negative 1 grams per second. Right? And when you take 10 to the negative 1 and you convert it to decimal, and in decimal form, that number is 0.1 grams per second. So their calculations are correct, but for some reason, whatever the publisher is or whoever edited it just tried to fit it into a box and just made a disaster of it. So in any case, this is where they got this number here, this 0.1 grams per second. Now if we go ahead and see if we can't see where we finally get to the end here. And we say, well, all right, so we got 0.1 grams per second, that's fine. Now because we assume that the input and output of the MTB are equal, so if we assume that the MTB is leaving the lake as quickly as it's coming in, then it's the input's also 0.1 grams per second. So we'll go ahead and assume that. These are assumptions, and anytime you make an assumption, of course, you're leaving yourself open for error, and that gets taken into account in any scientific endeavor. So you have art of MTBE is S divided by F. That's 10 to the 7th grams. Where do we get 10 to the 7th grams? Well, that's the total volume of the lake. Remember, 10 to the 7th was our reservoir size. That's what S means, right? In this case, our reservoir is the amount of MTBE that we had calculated in the first part of the problem. The amount of MTBE was 10 to the 7th grams, or let's see if I can remember correctly. 10 to the 7th grams. I don't have to rewind this or somehow restate it, but 10 to the 7th grams, I believe, or 10 to the 4th kilograms, or 10 metric tons of MTBE. That's the reservoir, right? And we know that the flow is, or the rate of transfer is 0.1 grams per second. So that's going to equal, when we do the division of 10 to the 7th divided by 0.1, it turns out to be 10 to the 8th seconds, because grams cancel out. But let's do the math to make sure, because things have been messed up the whole day here. So 10 to the 7th grams, and we're dividing it by 0.1 grams per second. So let me rewrite that as 10 to the 7th grams at times, or divided by 10 to the negative 1 grams per second. So that's equal to 10 to the 7th grams divided by 10 to the negative 1. Well, that's times second, right? Over 1. Remember, we inverted. What did we do? We inverted this and multiplied, right? So these two, then, that's 10 to the negative 1 grams. Grams do what? They're going to cancel out. And anytime you divide, you're subtracting. So negative, you have 7 minus negative 1 equals 10 to the 8th. And what is the unit? Seconds. And that's up here. So, all right. So 10 to the 8th seconds is correct. So we're good. They did this correctly. Yay. And if you did a conversion of seconds to years, we would do, and you can look at page 48 in Art of Water in the Big Lake, and you can see that we have 31,536,000 seconds in 1 year. And if we're looking at, we have 10 to the 8th seconds, what we would want to do is take, if we want to convert how many seconds we have in a year, we just take 10, let's go do that in blue then, 10 to the 8th seconds, and we're going to go ahead and multiply that times 1 year. How many seconds in a year? We have 31,536,000 seconds, and seconds cancel out. And if we do that number, we go ahead and calculate that out, equals indeed 3.17 years. And of course it's rounded off. It's 3.17097919, etc., etc. But in any case, 3.17 years, and they match up, and that math is correct. And then what does all that mean? Everything we just did, all these conversions, all these numbers, is that, as we suspected, the art of water is the same as MTBE. And if it's the same, then it suggests that the art is actually soluble in water. It's not in the soil. If it was in the sediment at the bottom of the lake, then obviously it's not going to leave the lake as quickly as if it were easily soluble in water. All right, so that's it. That was that whole art thing. I hope it helps you with your project that you're supposed to do. You can see there's a lot of conversion factors, and you can see they made a lot of mistakes in the book. So it wasn't you; it was the book that was wrong. I'm going to go ahead and say the book is wrong. Their typos are they make it difficult to follow, and then they tell you to look up some conversion factors, but they're using incorrect factors all throughout the whole process. So just go ahead and stick to what you know, and I think this should be more easily understandable, and we can go over it if we have to in class. All right, have a good one.